In the previous videos, we learned about the triclinic crystal system and its point groups. A point group consists of symmetry elements. Each element has a corresponding symmetry operation. Symmetry operations for point groups include rotation, reflection, and inversion. Every point group is assumed to have the identity or do-nothing operation, because every object looks the same after doing nothing to it. Point groups do not consist of operations, but rather symmetry elements. The element for a rotation is an axis, for a reflection is the mirror plane, and for an inversion is the center of inversion. A rotation axis is just a line around which the object rotates. A mirror plane separates two identical but opposite halves of an object, and a center of inversion causes every point to go to the opposite side of the center of inversion, reflecting the entire object in all three dimensions simultaneously. Every symmetry element in a given point group passes through the center point of the object or arrangement of objects, leaving that one point unchanged after applying all of the symmetry operations. This is where the name point group comes from. It's important to remember that performing the inversion operation creates an identical but opposite version of the original object, where one cannot be made identical to the other by rotations alone, just like a right and left hand. Reflection does this too. When an object or face of a crystal is rotated, its chirality or handedness is not affected. Monoclinic point groups have only two-fold rotations. These are rotations that make two stops at equal angles on their way around one full rotation. So a 180-degree rotation to the opposite side, and then another half rotation back to the starting point. Only 2, 3, 4, and 6-fold rotations are present in crystallographic point groups. This is because the unit cell has to be able to stack repeatedly, without overlapping or leaving any gaps. Simplifying our visual to 2 dimensions, we see that only 2-fold rectangular shapes, 3-fold triangular shapes, 4-fold squares, and 6-fold hexagonal shapes can be stacked without overlapping or leaving any gaps. 5-fold pentagons cannot be stacked to form a crystal, because they will always leave gaps that are too small for another pentagon to fit into. The exact same logic applies to 7, 8, and all higher order rotations. Next time we will learn about the 3 monoclinic point groups and their precise combinations of symmetry operations.